Hey folks, we are starting day 15 today. This is spanning trees. Before I get started, let me just remind you that you have an assignment that's due on Friday. So come by my office hours tomorrow at 3 o'clock if you've got questions about it, or drop me an email. I'd be happy to talk about it with you. Let's go ahead and get started. Let's let G be a connected graph. So we're requiring this to be connected, but maybe not a tree. So we could have cycles in this graph. A spanning tree of G is a subgraph, which is a tree and includes every vertex of G. Um, so let me give you an example of a spanning tree. Let's say this is our original graph here. This is not a tree because of these cycles that we have, but this subgraph here in red is a spanning tree. It is, um, here's your parent, here's the child, and then so on and so forth. Um, it doesn't contain any cycles. It's just, nodes and edges and leaves. Um, and it omits this edge and this edge here so to avoid completing the cycles. That's the idea. Um, so we have what's called a spanning tree here. It spans the entire graph. We can get to every vertex just using the red edges, and we don't have to have the non-red edges, the black edges, for connectivity. They provide some redundancy in the network, but they're not absolutely necessary. A weighted graph is a graph in which each edge has a weight that represents some cost, and it could be a monetary cost, it could be a cost in terms of memory or speed or CPU or some kind of cost that's associated with traversing that edge. So if we look at this example here, this is a weighted graph. Every edge has a certain um, weight attached to it um, that's involved in this. Um, the question that we want to ask is to find a minimum weight spanning tree for the graph. Can we create a subgraph that allows for any node to get to any other node, but includes only the least costly edges? And we have two different solutions to this problem today. One's called Kruskal's algorithm, and one's called Prim's algorithm. Um, this is not even pseudocode, but this is sort of the idea behind Kruskal's algorithm. Is we're going to build a list of edges that is initially empty, and we're going to choose a least expensive edge and append it to this list. Um, and then check to see if at this point all the vertices are reachable. And if it is, we stop. But as long as some vertices are unreachable, then we will choose a least expensive edge that extends the selected edges without creating a cycle, even if it creates a disconnected graph. Um, and keep doing that as long as some vertices are unreachable. Once all vertices are reachable, as long as we have obeyed this condition that we don't create cycles as we choose edges, we will get a spanning tree when we're done. Okay? So what we're going to try to do here is use Kruskal's algorithm to find a minimal spanning tree for this graph. So my tree, the selected edges, starts out empty, but I'm going to start by picking, look at all the weights and pick the smallest weight I can find, and the smallest weight I can find is 10. So we're going to pick that edge first. So we're going to add CD to the graph. Okay. All right. And then we're going to check, can I reach every vertex? And the answer is no, I can't reach every vertex just using CD. So I now look for the cheapest edge I can find, and I see a tie. There's a 20 here and a 20 here. If I have a tie, I just pick one. So I could pick either CE or ED. I'm going to pick CE. All right. And then that adds this edge to my list. Can I reach every vertex from here using just the red edges? And the answer is no. So now I go through the list again and I look at the cheapest vertex that is still out there. That would be ED now. But ED creates a cycle, and a tree can't have a cycle, and so I can't ever use this edge because it'll create a cycle, so I rule it out. So now I look at the remaining graph for the cheapest edge I could find, and it's way up here at GH. It doesn't create a cycle, so I'm going to add GH to my list. At this point, my red edges are not connected to each other. I have a disconnected set of red edges, and that's okay. We're just going to keep going. Is it possible to reach every vertex using just the red edges? And the answer is no, so I keep going. The next cheapest edge is the 30. This is from F to G. So we did this one third and this one fourth. And I still can't reach every vertex, so the next cheapest edge is the 35 over here. That's from G to B. And we got that one fifth. B. And we still can't reach every vertex. So then the next cheapest edge is going to be the 40 from B to E. All right. The next cheapest edge after that is the 45, but 45 creates a cycle, going from F to E to B to G and then back to F. And so I rule out the 45. I can't use it if it creates a cycle. So my my next cheapest edge is the 50, which is from A to B. We do that one seventh. And it turns out at this point, I can reach every single vertex. I have a connected graph with no tree with no cycles, and so I don't even have to look at the 60 and the 95. At this point, I found the cheapest tree that I can that will connect through the entire graph. Okay, are we good? So that's how Kruskal's algorithm works. Pick the smallest weighted edge you can, check to see if it will create a cycle. If it does, rule it out. If it doesn't, add it, and keep going until you can reach every single vertex. All right, let's try another one. Let's do Kruskal's algorithm on this graph here. So again, my selected edges starts out empty. Selected edges, but I'm going to start by adding GH. That has a weight of 2. That's the smallest edge I have. And I'm going to just keep going until I can't, until I have every vertex covered here. So the next thing I'll have to do is add AB. I have a tie now for 4s. So GC or GF. Well, it doesn't really matter because if I add GC, then at the next round, I add GF because this time the other edge in the tie doesn't close out a cycle. So I end up adding them both. All right, I have a tie for 5s. If I add BC, then I can still add CD, so I can add both of them. I have a tie for 6s, but I can't add them both, because if I add them both, that's going to create a cycle going from C to D to E to F to G and then back to C. So I can't use both of them. I do have to get to E, so I have to pick one of them, but it doesn't matter which one we pick. So I'll go ahead and pick DE. But I made that pick random. Okay. All right. So then I cannot use this 6. The next lowest edge is a 7, but I cannot use the 7 because it will close out this triangle, C, G, F, and then back to C. I cannot use the 8 because it will close out a cycle. I cannot use the 9 because it will close out a cycle. But I didn't need to check 7 and 8 and 9 because I actually already have a tree here. Every vertex can be reached with the red edges that I have. And so at this point, we can stop. Okay. All right. Krebs' algorithm is a little bit different. Prim's algorithm has a slightly more complicated choosing rule here, but it never creates disconnected networks along the way. You always have a network of red edges that's connected. In this case, we have to choose a least expensive edge in which at least one of the vertices is selected and one of them is unselected. Okay? And then append that edge to the selected vertices, to the selected edges. Okay? So let's try Prim's algorithm and see how it works. This is the same graph we did with Kruskal's algorithm a little while ago. This time we're going to maintain 2 lists. A list of selected edges and a list of selected vertices. So we start with the cheapest edge and add that to the list. So we're going to start with CD, and the selected vertices will be C and D. All right. So now I want to choose an edge that includes C or D and then goes somewhere else. So the edges that I'm allowed to choose are C to B. So this is a candidate. C to E, this is a candidate. And D to E, this is a candidate. That it includes C or D, includes one of the selected vertices, and extends out to a non-selected vertex. So I just have to consider these 3 edges, and I want to pick the cheapest edge among those 3. Not among the whole graph, but just among these 3. And since I have a tie, I just pick one, so I will pick C to E. And then that adds a new edge and a new vertex. E is now selected. Okay. All right. So now I look at the edges that will extend the graph. So C to B is still a contender. D to E is not a contender because DE will close up a cycle. E to B is a possibility. And E to F is a possibility. All of those start somewhere in the red, start with one of the selected vertices, one of the vertices that already have a red edge to, and extends out to a part of the graph that I haven't touched yet. Out of these 3 contenders, the one with the smallest weight is a 40, so I'm going to pick the 40. Now, at this point in Kruskal's algorithm, we would have gone up here and picked the 25. Prim's algorithm does a little bit of extra work, but it guarantees that the network we build is connected while we build it. We don't have these disconnected parts. So we're building this network and it's still connected. Okay? So we're now EB, and B is now selected. All right. So now we're looking for a vertex, for an edge that will extend the graph. CB is no longer allowed because that will close up a triangle. So what is allowed? I can go from B to A, from B to G, from B to F, or from E to F. Those are the ways that I have extending the graph. I'm only allowed to look at those 4 edges, and the one that's the cheapest is the one from B to G. So we add B to G, little edges, and G is a selected vertex now. All right. So now I look at the ways of extending the graph. I can still go from B to A, from B to F, to E to F, but I can also go from G to H or G to F. Any of those edges will extend the graph. The cheapest one is the one from G to H. And we get H. All right. The cheapest edge now is the one from G to F. So F is now selected, and now we cannot choose the 95 or the 45 because those will close up a loop. But we can then add B to A. And that's the reaches the last vertex in the graph. And so this list of selected vertices, A, B, C, D, E, F, G, H, includes every vertex. And it turns out we get the same results when we're done as we get with crucifixes. It's not that prims and crucifixes gives me different final answers. It's that they give me, prims does a little bit of extra work by narrowing down all of the edges to a list of candidates. But at every stage, I have a connected set of red edges, so that if I'm actually implementing and building this, the red edges will never be disconnected, form disconnected sets. So, all right. Let's try this other example here. Using Prim's algorithm. We always start with the cheapest edge. So that's going to be G to H. So selected edges. Excuse me. Will include GH, and the selected vertices will include G and H. Okay, now crucifixes would next go up here to this edge AB and add it, but Prims doesn't because AB and GH are not connected to each other. So Prims looks at the edges that come out from G and H and picks the cheapest one of those it can. Well, that would be the one from G to C or the one from G to F. We'll do G to C. All right, and now it looks for how many ways we can extend the graph from there. We can go from C to B, C to D, or C to F. But we can still go from G to F, and that's the cheapest. So that adds another edge and another vertex to our set. And now we can extend the graph by going from F to E. But this point, 7 will create, C to F will close the cycle, so that becomes ineligible. So my eligible sets now are eligible edges are HA, GB, CB, CD, and FE. So I have a pair of 5s. Those are my tie. I can pick either one of them. So I'm going to pick the one over here at CD. That adds a D to the graph, or D to a list of selected vertices. All right, and now that also gives me one more way I can extend the graph. I can go from D to E. So out of all of the ways that we can extend the graph, we can extend it from C over to B. That uses the other 5. And then this finally opens up the B to A edge. By the way, A has become ineligible at this point because that will close up a cycle. But we can do B to A. So there's our vertex, and now that makes 9 ineligible. And so we now have to pick one of the 6s. It doesn't matter which one. So this time let's pick FE, and that adds E to my list. And and now makes this edge ineligible because it'll close up the cycle. And so I get a spanning tree that includes every edge but doesn't include any cycles, and it stayed connected as we were building it. That's how Prim's algorithm works. Okay? So let's move on to another topic. If we have to store a graph online, one way we can do this is to store it using what's called an adjacency matrix, where I list the vertices in rows and columns, and I list the weights of any edges if there is a weight, and if they're not weighted, I could just use 1s and 0s to represent what's going on here. So if this is my adjacency matrix, this gives me enough information to rebuild the graph. I have 5 vertices, A, B, C, D, and E. I'm just arbitrarily just placing them around a circle. I see that A connects to B with a weight of 3. A connects to C with a weight of 5. All right. And A connects to D with a weight of 1. All right. B connects to C with a weight of 2. D connects to E with a weight of 4. So that's going to go down through here. All right. C connects to D with a weight of 3. C connects to E with a weight of just 1. And we've got one more edge. D connects to E with a weight of 6. Okay. And anything with a weight of 0 means that there is no edge. Okay. All right. So that's how an adjacency matrix works. We could store the information and build up the graph in the form of a matrix. There is some redundancy built into the matrix because BA and AB are in 2 different places in the matrix. But that just gives us a way of checking. Okay. If our graph is a tree, so this is trees only, we could do better than an adjacency matrix. Prufer sequence stores trees only, not other kinds of graphs, but it's really highly efficient. This took a 5 by 5 vertex graph and used 25 entries to store the graph entry. Now, it has some redundancy built in, but we're still using n squared entries here. Let's look at how Prufer sequence works. We have a tree with a bunch of vertices. We're going to start out by setting, let's just sort of draw an example here. So let's call these, say A, B, C, D, and E. All right. Oh, okay. So A, B, C, D, and E. We're going to set I equals 0. So I is equal to 0. And T is 0 is the entire tree, the whole tree. And the Prufer sequence P is going to be completely empty. So we don't have anything in the sequence yet. We're going to look for the leaf that has the smallest label. So in this case, since I was using letters instead of numbers, smallest might be earliest in the alphabet. So let's say B. Okay. Because it is a leaf, it has only one neighbor. It has a parent. Okay. We're not going to add B to the sequence. We're going to add the parent. So we're going to find the label of V's only neighbor and append that to the sequence. Okay. So first thing I'm going to do is go write an A. And now what I'm going to do is remove B from the tree completely. And now this is the tree 1. Okay. And I is now 1. So we're just incrementing and we're creating a new tree now. Okay. So we're going to do the same thing again. Now I have 1, 2, 3 leaves, but the one with the smallest value is A. What I'm going to do is I'm going to write down the parent of A and then delete A. Okay. Here's my graph now. All right. I look for the leaf that has the smallest value, and that's going to be D. I write down the parent of D and then delete D itself. Okay. And the last thing we see is that if we just have a single edge, then we stop. We have just an edge. Either one could be the leaf, either one could be the parent. It's you can't do anything once you have a single edge. And so here's my Prufer sequence. It's just ACC. That's enough to build back the original graph. Okay. How do we know how to build the original graph? Okay. So this information is on the later slides, but let's go through the process here. Okay. I have 3 entries in here. I'm going to add 2. So when we're reconstructing the graph, we're going to count P and add 2. The reason we're adding 2 is that we stopped when we got down to that single edge. And that single edge had 2 vertices. Those are the vertices. So I need 5 vertices. They're going to be A, B, C, D, and E. Okay? I look for the smallest letter that does not show up in the Prufer sequence. And the smallest letter that doesn't show up in the Prufer sequence is B. And so I'm going to match B to an A. So B gets matched up to an A. And now what I'm going to do is I'm going to cross off B and I'm going to go ahead and cross off A. Okay. B gets crossed out of the original list of vertices. It was the leaf, but A was the parent. And so we're going to, mark off the parent in the list of Prufer sequence here. All right. So then I look for the smallest vertex in my list of vertices that doesn't show up in my Prufer list, and that would be the A. So now A is connected to C. So A got connected to C. That actually makes A not a leaf in this case. It's the because it's also connected to B. But we're going to cross off the A, and then we're going to cross off the C. So now I look for the smallest vertex that's not in this list, and that would be D. And so D is going to match up to C. All right. And so we cross off D from this list, and we cross off C from this list. And when we are finished, we have used up the list. We're reminded that there was a single edge that was left. That single edge goes between the two vertices that are remaining, and those are C and E. And so that finishes up the reconstruction. So we can convert a tree to a Prufer sequence. We can convert a Prufer sequence back into a tree. Let's work through some examples here. Let's generate the Prufer sequence for this tree. All right. So what we're going to do is we're going to look for the smallest leaf. My leaves right now are 2, 6, 5, and 7, and 2 is the smallest one. I don't write down the 2, I write down its parent. And so the 2 goes away. Now, again, I look for the smallest leaf in the graph that's remaining. This time it's 4. I write down the parent of 4, and I cross the 4 off. Okay. Keep going. I've got down to 3, 1, 5, 6, 7. The smallest leaf, though, is 5, and its parent is 1. So now I've got 6, 3, 1, 7. The smallest leaf is the 6. Its parent is 3. Okay. Now I've just got 3, 1, 7. Smallest leaf is a 3, and its parent is 1. Now I'm down to a single edge. When I'm down to a single edge, I go ahead and just quit. And so my Prufer sequence has only 5 numbers in it, even though there were 7 vertices. I write down something for 5 elements, and then by the time I'm down to just 2 more, that's just 1 edge, and I quit. Okay? All right, so then this is the procedure for converting a Prufer sequence back into a tree. We talked about that a moment ago, but here's the procedure again, and it's a little cramped. We have a Prufer sequence of length k. We look at that, and then we add 2 more to our list of vertices. Those 2 extra entries represent the endpoints of the last line segment that we left out. Okay? We're going to set up some things to iterate through here. We let J be the smallest number in the list of L that doesn't appear in the Prufer sequence. So we're looking for a leaf, so it has to be one of the vertices, but it can't be a parent. And so we want to eliminate any of the parent nodes. So we find the leaf that goes up to it. K is just the first number in the list of parent nodes, and we're going to construct the leaf to the parent. So we're going to build an edge from vertex Vj to vertex Vk. Then we remove the J from the list of L, and we remove K from the list of parents. Okay, that creates some new lists, and so we increment I by 1. We go back to step 3 and keep going. Once we have used up all of the parents, there will be 2 vertices left in L because L has 2 extra entries. Those last two entries represent the line segment, the edge that we left out. And we'll go ahead and connect those and then stop. Okay. So let's try an example of building the sequence back into a tree. So we're going to rebuild the graph in the last example from its Prufer sequence. Let's go back and look at it. The sequence was 43131. All right. So we have a list that has two more entries than P does. P has 5 entries, so L is going to go up to 7. I look for the smallest leaf that is not also a parent. So 1 is a parent, but 2 is just a leaf. So 2 is going to be the thing that I'm going to match to 4. So we're going to draw an edge from 2 to 4. And then we'll cross off the 2 on the list, and we'll cross off the 4 on the list. Okay? So now we look for the smallest leaf that is no longer, that is not a parent, and 4 is no longer on this list. So 4 will be the smallest leaf, and it will connect to a 3. All right, so I cross off the 4, I cross off the 3. I look for the smallest leaf that is not a parent. My parents are 1, 3, and 1. So I don't use 1, I don't use 3, I'm going to use 5. And 5 is going to connect to a 1. Well, I don't have a 5 or a 1 on this graph. So I'll go ahead and put them in and connect 1 to 5. All right. So then, again, the smallest leaf that's not a parent. So 1 is still a parent and 3 is still a parent. So 6 is the smallest leaf that's not a parent, and that's going to be connect to a 3. So 6 connects to 3. And we cross out the 6 and we cross out a 3. Now my leaves are 1, 3, and 7. My parent only has a 1 in it. So now 3 is a leaf that's no longer a parent. And the 3 will connect to a 1. Okay. And so we cross out the 3. And we cross out the 1. And I don't have any parents left, but I still have these 2 vertices left, 1 and 7. That forms the last line segment, the last edge that wasn't written down in the first place. Okay, and so that rebuilds the graph. It doesn't look identical to what we had before, but it's got exactly the same connectivity. Okay, let's try another one. Let's construct this tree here, 175771. So these are my parents. My leaves start at 1 through 8, because there are 6 parents here. I add 2 and get me up to 8. I look for the smallest number in L that's not in P, and that's a 2. So 2 connects to 1. And now 2 goes off of this list and 1 goes off of this list. Again, I look for the smallest L that's not in P. That's going to be 3 this time. And 3 will connect to a 7. Now the 3 goes off and a 7 goes off. And I have 2 disconnected edges. That's okay. We'll connect them later. 4 is not on this list, so 4 goes to 5. Okay, so 4 goes to 5. 1 is on this list. 5 used to be on this list, but we've crossed it out, so 5 is no longer on the List of parents, 5 will connect to 7. That takes care of 5. That takes care of 7. 6 is a leaf that connects to 7. All right. Now, what happened here? 1, 6, I've crossed out the 6. 1, 7, and 8 are the leaves that are left. 1 is still on the parent list, but 7 had been a parent 3 times, but it's not on the list anymore. So 7 will be the child and 1 will be the parent. This is a 1. And now the 7 goes off and the 1 goes off. And now I don't have any parents listed. I still have these 2 leaves, 1 and 8. They have to connect to finish off the tree. Okay? All right. So we've looked at Kruskal's algorithm, we've looked at Prim's algorithm, and we've looked at Prufer's algorithm. Kruskal's and Prim's find a minimum spanning tree. Prufer's algorithm stores a tree with k vertices in it using only k minus 2 values. So it's actually smaller than the size of the tree. It's super efficient in terms of storage. All right. Y'all take care. See you around.